Hello everyone. Now we will discuss on the topic transmission of pollutants in environment. This is the part 1 of this topic. In the last class we have seen that pollutants are generated in the environment through different sources and it gets entry into the human body, other living organisms, etc. And for this it needs to be transmitted from the point of generation to the point where the living organisms are existing. So, the transmission of pollution is very important. If pollutant may be generated, but it is not transmitted to the particular person or living organism. So, then he or she or it will not be affected. Okay. So, the transmission is very important and transmission can take place through air, through water or through soil. Okay. So, we will be discussing now transmission in air and then air pollution dispersions, how the transmission is taking place, how the dispersion of the pollution taking place, how the pollution is moving from one place to others in the atmosphere. So, that part we will discuss and then diffusion and advection for dispersion of air pollutants. We will see the major two mechanism for the dispersions, that is one diffusion and another is your advection. We will also see that this process is influenced by the stability of the environment. So, we will also discuss on the atmospheric stability and dispersion and air pollution emission plume. So, when the air is polluted, that means emission is coming entry into the atmosphere through a stack from a chimney say. So, how this will be going downstream. Okay. So, whether the plume will go up or whether it will come down. If it goes up, then there is no risk, but if it comes down, then it will be risky. So, people will be more affected. So, those things, the different types of plumes we will discuss and modeling of air pollution dispersions. We want to predict, say here we have an industry and pollution is generated. So, after 1 kilometer or 5 kilometer, what will be the concentration, okay, so of pollutants in the atmosphere at certain height. So, that we can measure and transmission of water, that we will discuss in the next class. So, we have seen that dispersion of air pollutants can take place through diffusion and advection. What is diffusion? Diffusion means pollutants are moving from one place to other place due to the difference in the concentration. So, concentration gradient is the driving force for this transfer, and in case of advection we will see the flow of wind is helping the transfer of the pollutants from one place to other place. So, there are two major mechanism, diffusion and advection. So, pollutants are distributed through diffusion, okay. There is movement due to concentration gradient and advection movement due to bulk motion of air, just we have discussed. Now, advection on weather maps is dependent upon two factors, that is the strength of the wind and the direction of the wind. For example, say we have here 68, 68, 68, 70, 66, 60. So, as we go up, so our temperature of the atmosphere decreases, okay, that is lapse rate. Now, say for a certain height, we are assuming that horizontally all points are having same temperature. If we go up, temperature will reduce, like say here 70, here 68, here 66, here 64. So, if wind blows this direction, okay, then what will happen? If wind blows this direction with same directions with lower speed, what will happen? If wind blows like this direction, what will happen in case of advection? So, here maximum advections we can get, because advections will help to upward movement basically, and then here it is lesser, and in this case there will be no, because this will be parallel flow. So, layers will not be mixed, no turbulence will be there. Okay. So, that this is the case. So, maximum advection in case of A we will get, advections lower than A in case of B, and C will have no advections, okay, because wind speed. So, it is clear that wind speed will influence and wind direction will influence the mixings of the different layers of the atmosphere across the height. Okay. So, that is the the advection which we are talking about. And then the dispersion is influenced by the wind speed, its directions, and hence the atmospheric stability. But stability is nothing but that resist the upward flow. Now, atmospheric stability is a measure of the atmosphere tendency to discourage or deter vertical motion, and vertical motion is directly correlated to different types of weather systems and their severity. Okay. So, wind velocity, temperature, turbulence, humidity, rainfall, etc., influence atmospheric stability. As a result, it also influences the dispersion of pollutants. Pollutants dispersion is also influenced by the stability conditions of the atmosphere. So, there are three types of stability conditions, like say unstable, maybe stable, or maybe neutral. So, an unstable atmosphere will enhance or encourage the vertical movement of air. So, if vertical movement is encouraged, means it is unstable. A stable atmosphere will suppresses the vertical motion, or it will resist the vertical motion, and neutral atmosphere will neither suppress nor enhance vertical motion. So, these are three different atmospheric stability conditions we can get. Now, if we assume that air parcels is going up, okay, so inside its condition is different from the outside. It may be possible that inside is becoming less cooler with height, but outside environment is becoming more cooler. So, that is lapse rate. If we go up, temperature will decrease with the height. So, that is lapse rate. So, when it is when the lapse rate we consider for the actual environment, that is environmental lapse rate, and if we consider under certain conditions that we have a parcel, it is going at air parcel, it is moving up, and when it is moving, it is not taking any heat or energy from outside. So, adiabatic conditions, if it goes up, in that condition what is the lapse rate, if we can measure, that is called adiabatic lapse rate. So, by comparing these two lapse rate we can quantify that what is the conditions, the stability conditions, that is unstable, stable, or neutral. So, now if an air parcel is warmer than its surrounding environment, then it will be less dense than its surrounding and will rise like a hot air balloon. This is unstable air and has the potential for creating storms. If an air parcel is cooler than its surrounding environment, then it will be denser than its environment and will sink. Denser means less volume. So, outside will be outside temperature higher. So, that will be expanded, and so the our parcel will be squeezed, that is the case. And this is stable air, which generally leads to clear skies, and if an air parcel is the same temperature as its, then the neutral atmosphere we can get. So, if we have air parcel and outside environment, both are having same lapse rate. So, then we will get the neutral condition. So, stability is dependent upon the dry and saturated adiabatic lapse rates and the environmental lapse rate. So, one is environmental lapse rates, another is your adiabatic lapse rate. So, adiabatic lapse rate means a balloon or the parcel which is going up, we are considering it will not take any heat from the outside when it will goes up. Now, that is adiabatic expansion or contraction, whatever may take place, but it will be happening in adiabatic condition. So, that is called. Now, if it is that the air may be dry or may be wet. So, depending upon the dry and wet conditions, we will be getting dry and saturated adiabatic lapse rates. So, environmental lapse rate, the rate at which air temperature changes with height in the atmosphere surrounding a cloud or rising parcel of air. So, the overall average rate is decrease of about 6.5 degree centigrade per kilometer, where the lapse rate of temperature is negative. As you know that we go up, the temperature reduces, that is why negative lapse rate, and inversion is said to exist, where the lapse rate of temperature is negative, that is temperature increases with height, and inversion is said to exist. The word adiabatic means that no outside heat is involved in the warming or cooling of the air parcels, just we have discussed, and dry air cools at about 10 degree centigrade per kilometer. The dry adiabatic lapse rate is, while moist air usually cools at less than 6 degree centigrade per kilometer, that is moist adiabatic lapse rate. So, these two adiabatic lapse rate we have. Now, ambient lapse rate is equal to adiabatic lapse rate. So, then that is dry adiabatic lapse rate, then it is neutral. If ambient lapse rate is greater than, that is dry adiabatic lapse rate, or temperature falls faster in that case, so unstable or super adiabatic, and if the ambient lapse rate is less than the dry adiabatic lapse rate, so it is stable or subadiabatic condition. So, these are the different conditions we can quantify the environmental stability condition. And because of these different stability conditions, when the gas comes out from a stack, they are dispersed in different fashions. Like say we can get somewhere coning. So, this is coning, we can get looping, we can get fanning, we can get fumigation, we can get lofting. So, what is happening in case of coning? So, here this dotted line is our dry adiabatic lapse rate and solid line is your environmental lapse rate. So, what is happening in this case? Both are parallel, having same, that means the environmental lapse rate is equal to dry adiabatic lapse rate same. So, there will be neutral environment. So, when a pollution is emitting from this stack, so it will not go up nor go down. So, it will be uniformly distributed both way. If you take the center of it, so it is uniformly distributed. So, this is a coning type of plume, we get this type of situation when the neutral environment is there, neutral atmosphere is there. But here we see this is dotted is our adiabatic lapse rate and this is our natural environmental lapse rate. So, this if we consider some point here certain height, so 0 to this height. So, for this we are changing this temperature here and for this case we are getting this temperature. So, del T by del H for same Z we are getting more del T in case of actual lapse rate. So, actual lapse rate we are getting more del T. So, del T by del T, that is lapse rate is more. So, when environmental lapse rate or atmospheric lapse rate is more than the dry adiabatic lapse rate, then we get this system is unstable, and if it is unstable, then what will happen? The pollution which is emitting here, that will goes up, and when it is goes up, and again there will be some chance and coming down also, because there will be some turbulence, and then this type of looping plume we will get. Other way, say another example if we see here. So, here we are getting inversion, that is with height increase the temperature is increasing not decreasing. So, inversion is there. So, in case of inversions we can get the fanning, the pollutions will not be able to come down, where the people are here. So, the pollutants are not coming here. So, these people are relatively safe. Now, another is your lofting. So, lofting here the first part from this part is your inversion and second part is this one. So, here what is this, if you make a parallel line here. So, you are getting the rate of this is more than this one. So, even unstable is there. So, first part is your this first part is your inversions, the from bottom to certain height it is in inversion, and then above that it is your unstable. So, in that case there will be less chance of the pollutants to come into the environment. Okay. So, that is this is called lofting, and another type of plume can be available because of this type of environmental condition. Okay. So, in this case you see this if we take this point, so 0 to Z same Z, these are having del T. So, this is unstable, and then we are getting this one is your again inversion. So, unstable inversion. So, this will give us the fumigation. So, these are the different types of plumes we get, and we see that fumigation is one of the most dangerous plume types, when people will be mostly affected by the pollutants being emitted in the stack. Now, we will see how to model this dispersion process. Okay. So, point source Gaussian plume model is mostly used. There are many approaches, people have tried to develop some model to predict the concentration of pollutants after certain distance downstream of the wind and from the location of the emission So, people tried to develop different models. So, one is your point source Gaussian plume model is very important, which is mostly used, and the Gaussian model is perhaps the oldest and perhaps the most commonly used model type. It assumes that the air pollutant dispersions has a Gaussian distribution. That means, this is the center point. So, it will be dispersed like this. So, maximum concentration will be having, then it will be decreasing like this. So, this is the maximum concentration and it will decrease both side. So, it assumes that the air pollutant dispersions has a Gaussian distribution, meaning that the pollutant distribution has a normal probability distribution like this, and the primary algorithm used in Gaussian modeling is the generalized dispersion equation for a continuous point source plume. So, this is a continuous point source plume. So, how this will be distributed at different positions, this can be derived on the basis of this model. This is the height of the chimney, and here plume is generated. So, this is plume height del h. So, small del h is the plume height and h is the stack height, physical height. So, this h plus del h, that is capital H, this is the actual working height of the emission. This is a virtual point source and this is the center point of it, and then instantaneous plume boundary it is told, and this is wind speed, okay, and this is time averaged plume center line, and this is time average plume envelope. So, this is the different parts to describe this Gaussian plume model like this. It can have x, y and z direction. We are only interested at ground concentrations, as we are interested only people are here at the ground. So, if this is the point, maybe here, maybe here, maybe here, anywhere position the people may be available. So, at that position x, y will change, and z we are not concentrated, because pollutants has to be available at the ground to make it impact on the human health. So, model structure and assumptions, some assumptions are there for this, that is pollutants release from a virtual point source, pollution is released from a virtual point source, it is a point source. So, that it is easy to identify, and then it is a constant emission rate of emission is not changing with time, and advective transport is by wind is responsible for the advection, and dispersive transport, that is spreading, follows normal, that is Gaussian distributions away from the trajectory, and wind speed constant with time and elevation. Pollutant is conservative, non-reactive, say it is not the fact that now the pollutant is present, but after some time it will be converted to other form, not like this. We are assuming that pollutants are conservative in nature, and train is flat and unobstructed, and uniform atmospheric stability. It is also assumed that atmospheric stability is not changing from certain place to place. So, that is why these are the major assumptions on the basis of which the expressions has been developed, and the expression is like this: concentration at x y position, that is equal to E by pi s y s z u exponential minus half y by s y to the power square into exponential minus half h by s z to the power square. So, this is the expression, and in this expression C is the concentration at ground level at point x y, and then E is the emission rate of pollutant gram per second unit, and s y s z plume dispersion standard deviations in horizontal and vertical directions respectively in meter, and U wind speed at stack effective height. So, capital H, that is m per second, meter per second, and x is distance downwind in m meter unit, y horizontal distance from plume center line in meter, and h is effective stack height in meter. So, these are empirical relationship. So, we need to take the formula in the same unit only. And how to find out the effective stack height, that capital H, that is equal to small h plus del h, we have seen in the previous slide. So, here h is the effective stack height and h is the height of the physical stack and del h is the plume rise. Holland's formula, how we can determine this del h then? Del h, that is plume rise, how we can measure? So, that is equal to B s by u d into d multiplied by 1.5 plus 2.68 into 10 to the minus 2 into p into T s minus T a by T a into d. So, this is the expression. In this expression del h is nothing but the effective, but the plume rise in meter, and V s is the stack flue gas velocity meter per second, and d is the stack diameter at exit, the stack diameter in meter, u is the wind speed at the stack height, and then p is the pressure kilopascal. If kilopascal, then 10 to the minus 2, this constant will be there, and Ts is stack temperature flue gases, that is your in K, and Ta is the ambient air temperature at K. So, stack temperature and air temperature, ambient air temperature Ts and Ta respectively. So, these are the expressions to calculate the del H value. Now, the stability conditions may be of different and different types of stability we can get, and we have seen that the people have worked and on this area and the information is available. The if surface wind speed at 10 meter height is less than 2 meter per second, and then if daytime or night time the people consider, if daytime with strong sunlight or moderate radiations, okay, and then slight radiation. So, then different types of stability condition. Similarly, for night also it may be covered, it may be partially covered with cloud. So, in that case different stability conditions are obtained, say depending upon the wind speed at 10 meter height in meter per second, and day and night condition, whether the sun is very sun shining is very strong or it is cloudy. So, all those things are considered and different stability condition A to F has been defined. So, A is extremely unstable, B is moderately unstable, C slightly unstable, D neutral, E slightly stable, and F moderately stable. So, these are the different conditions which are defined, and out of these different stability conditions we can get the value of S y and S z which are available in literature, as the many people have worked on it and these has been accepted for applications. So, these are some distance from source, if we measure, if we know the stability condition for that particular case, we will get the value of S y. Similarly, we can get the value of S z if we know the different stability conditions from this graph. So, these graphs are already developed by many research and those are available for us now for our application. And wind speed, I told you that at stack height wind speed, and somewhere we defined u in the table that at 10 meter height. So, we have to convert it to at stack height. So, u2 is equal to u1 into z2 by z1 to the power p, this is the expression which is used to calculate the wind speed at stack height. At 10 meter height we know, but at stack height what will be, that will be determined by this formula, and in this case p value will depend on the stability conditions. If we see here, if we have stability class A, B, C, D, E, F, and it may be rural area, it may be urban area. So, depending upon this area, so these values are defined, people have worked and on the basis of experience these p values have been recommended for computation or for prediction, that is wind speed correction. And here where ux, that is u1 u2 we have shown. So, ux in general term wind speed at elevation zx and p is the empirical constant. This p will be used to determine the value of u2. Now, for example, so a stack in an urban area is emitting 80 gram per second of NOx NO. It has an effective stack height of 100 meter. The wind speed is 4 meter per second at 10 meter. It is clear summer day with the sun nearly overhead. Estimate the ground level concentration at 2 kilometer downwind on the center line and 2 kilometer downwind 0.1 kilometer of the center line. So, x and y value is given in the case 2 and in the case no value is given. So, what we will do, what will be the first step? So, we have to determine the stability class. So, how can we determine the stability class? For the determination of the stability class, I have shown you some table. So, where the speed at 10 meter height is important. So, in our case 4 meter per second at 10 meter height it is given. So, we will be considering that the wind speed is 4 meter per second at ground surface. It is a clear summer day with sun nearly overhead, that means strong sunshine daytime and strong sunshine. So, if we see this table, so here we will get 4 meter per second, that means 3 to 5 this one, we have strong radiation, solar radiation, because middle of the day and clear day. So, this will be of B type of stability, and if it is B type of stability, then what will be our job? Our job will be to find out the value of P. So, P we have another table we have discussed. So, in this case we are having B. So, B will be having this 0.15, P equal to 0.15. So, in this case if we put this value to get the value of wind speed at our stack height, then u 2 will be u 1 into z 2 by z 1 to the power p, when u 1 is 4 and z 2 is your how much? It is given 100 meter stack height, effective stack height is given. So, we do not need to calculate the effective stack height, it is already given physical stack height plus plume rise. So, that is given 100 meter. So, that formula we do not need to know to determine the value of del h, and then to make it add it with h to get h equal to small h plus del h, that is not needed. So, we are directly getting the value of P, and then we will be putting this P value here, Z 2 value is given 100 and this is 10. So, to the power 0.15. So, it is becoming 5.65 meter per second. So, this is the wind speed. So, now we will put it into the formula, but before that we need the S y and S z values. So, S y and S z values we will be calculating it from the graphs available. So, in our case, what is the case? We have the B type of stability. So, this is our B type of stability graph at this distance downwind. So, downwind, what is the distance that we have to see? It is given that distance is equal to 2 kilometer downwind. So, 2 kilometer in the case of 2 kilometer, and in the second case 2 kilometer downwind, 0.1 kilometer of the center line. So, we will be using this formula to find out for 2 kilometer. So, this is our y s, because this is downwind distance 2 kilometer and s y values are becoming here this point. So, 290 we are getting. So, similarly, S z for this A case we are having 2 kilometer, we will go here for B type of stability we are getting 220. So, S y and S z values we are getting by that way, S y 290, S z 220. Then we will put this the values, we have formula C x y equal to E by phi S y S z u exponential minus half y by S y to the power square into exponential minus half h by S z to the power square. So, in this case E is equal to 80 gram per second. So, that is 80 gram per second, it is mentioned, and then pi value we know, and 290 S y, 220 S z we have calculated, 5.6 u we have calculated, and then y value is 0 in this case, because it is only 2 kilometer downwind in the center line. So, it is off from the center line, it is not given. So, y equal to 0. So, we are giving this one, and height is equal to 100 divided by 220 to the square. So, this expression we are getting, that will be the concentration at 2 kilometer away, that is x 2000 and y equal to 0. So, here we are getting, by simplifying, we are getting 6.43 into 10 to the power minus 5 gram per meter cube, or 64.3 microgram per meter cube. So, this is the concentration which will be available at 2 kilometer downwind, and in the second case we have to find out for 2 kilometer downwind and 0.1 kilometer of the center line. So, we have x equal to 2000, y equal to 0.1 kilometer. So, that is equal to 100 meter. So, we are getting the concentration here A C 2100, that is equal to 80 divided by pi 290 220 into 5.6 into exponential minus half of y value is not 0 now, y has some value, that is equal to 0.1 kilometer, that is 100 meter. So, we will put it 100 meter and then 290 then a square, and exponential again height is also 100. So, we will put the value of 100 and then 220 square. So, then we are getting this expression, and by simplifications of this expression we are getting the values of C 2100 equal to 6.06 into 10 to the power minus 5 gram per meter cube, and that is equal to 60.6 microgram per meter cube. So, now we are able to determine the concentration at these two locations. So, up to this in this class, thank you very much for your patience.